A heavy truck is much harder to stop than a small car moving at the same speed. Okay, this we know, we see it every day. It's much harder to stop a truck than it is a small car, especially if they have the same momentum. We state this fact by saying that the truck has more momentum, so its momentum is larger than the car itself. Momentum we use as P, so P is greater than P for the truck is greater than for the car. And by momentum, we mean what is inertia in motion. So momentum has to do with the mass and motion. Okay, so depending on the mass and the velocity of that object, okay, or P is equal to m times v. Okay. So the truck has a larger momentum due to its larger mass. If the momentum of an object changes, then either the mass or the velocity has changed. Okay, most often it's going to be the velocity that changes since acceleration is occurring. Okay? What produces that acceleration though? So if there's a velocity change, there must be an acceleration. What's producing the acceleration? Force. Okay, so the force there must be a force on the object that's changing the acceleration. So if there's a force acting on that object, okay, let's say there's an unbalanced force this way, so a net force in this direction, there must be an acceleration in that direction as well. The greater the force on the object, the greater the acceleration, which also means the greater change in momentum. Okay, so the key here is the change in momentum. So the amount of time the force acts also changes the momentum. So the longer a force is acting on an object is going to change its acceleration further, which changes its momentum. And so if you are pushing a car, so here's my car, it's gotten stuck, or you've stalled out your car, whatever, it doesn't matter. You need to move that car, so you're pushing the car. So if you apply a brief force, so a very small force, to an automobile, you produce a change in its momentum. So you're going to change P if you apply a force. Okay, now if you apply the same force over a longer period of time, so the same force over a long period of time, so a lot of time, okay, so we apply a little force, or a big force over a little amount of time, we have a change in momentum. But if we apply the same force over a larger time, we have a much larger change in momentum. Based on these two facts, we know that the force and the time that that force is applied is going to be proportional to the change in momentum. The change in momentum is the impulse. And so impulse is equal to the force multiplied by the time. The greater the impulse exerted on something, the greater the change in momentum. Okay, so impulse is the change in momentum. So the equation for impulse so as I said, the impulse is also the change in momentum. So we have the force multiplied by the time is equal to the change in momentum. To increase the momentum of an object, it makes sense to apply the greatest force possible for as long as possible. A golfer teeing off and a baseball player trying for a home run do both of these things when they swing as hard as possible and follow through with their swings. Following through extends the time of contact. So the forces involved in impulses usually vary from instant to instant. For example, a golf club that strikes a ball exerts zero force on the ball until it comes in contact. Then the force increases rapidly as the ball is distorted. The force then diminishes as the ball comes up to speed and returns to its original shape. And so when we speak of such forces in this case, we mean that the average force. If you were in a car that was out of control and you had to choose between hitting a concrete wall or a haystack, you wouldn't have to call on your knowledge of physics to make up your mind. Common sense tells you to choose the haystack, but knowing the physics helps you understand why hitting a soft object is entirely different than hitting a hard one. In the case of either hitting the wall or the haystack and coming to a stop, it takes the same impulse to decrease your momentum to zero. The same impulse does not mean the same amount of force or the same amount of time. Rather, it means the same product of force and time. So by hitting the haystack instead of the wall, you extend the time during which your momentum is brought to zero. A longer time interval reduces the force and decreases the resulting deceleration. For example, if the time interval is extended 100 times, the force is reduced to 100. Whenever we wish the force to be small, we extend the time of contact, hence the padded dashboards and airbags in motor vehicles. And so you hit an airbag in order to increase the amount of time that you are applying a force. So in the first case, so you're sliding into a haystack and you have some momentum, so a large velocity and a mass. Okay, so it's the same case for both. You have a large velocity and whatever your mass is. When you hit the haystack, as in the first case, you are applying a small force over a long time. So this case is much more safer. So we're applying a smaller force over a larger amount of time. Okay? Now, if you hit the wall, you're applying a large force in a small amount of time. Okay? This is why it's much worse to hit the wall. Applying a larger force is going to cause much more damage to your car than you would if you applied a small force. Okay? So in both cases, we have the same impulse, but different forces and times. Similarly, when jumping from an elevated position down to the ground, what happens if you keep your legs straight and stiff? Ouch! Instead, you bend your knees when your feet make contact with the ground. By doing so, you extend the time during which your momentum decreases compared to a stiff leg abrupt landing. The resulting force on your bones is reduced and it is much safer for your joints. When boxing, if you move into a punch instead of away, you're in trouble. So in the case to the left, the boxer getting punched in the face is moving away from that punch. So that's the direction of his motion, and in the second case, he's moving towards. So you can see that it's a little bit worse if you're moving into that punch as opposed to moving away. So in the first case, when he's moving away from the punch, okay, so there's just a little bit of a punch to the face. He's still getting punched, but it's not as bad. So as he's getting punched and he's moving away, there's a force applied, but it's over a long period of time. Now it's a short period of time in terms of the punch, but it's much longer in terms of this situation compared to the other one. So when you move into the punch, you're actually increasing the force and decreasing the amount of time for the punch taking place. So you can see that the larger force is going to hurt much more and most likely break his nose compared to the one that takes a much larger amount of time but applies a smaller force. So in both cases, it's the same impulse, but different forces being applied. If a flower pot falls from a shelf onto your head, you may be in trouble. If it bounces from your head, then you're in much more serious trouble. Why? Because impulses are greater when an object bounces. The impulse required to bring an object to a stop and then throw it back again is greater than the impulse required merely to bring the object to a stop. So if you want to bring, or if this flower pot falls onto your head and bounces, and then the force applied is much larger and the time that it takes if it was just to stop. So here's the bouncing and the stopping. you may be applying the same force, but in a much smaller time when it's stopping. Okay, so your impulse is going to be much larger when something bounces. Suppose, for example, that you catch the falling pot with your hands. Can you provide an impulse to reduce its momentum to zero? If you throw the pot upward again, you have to provide additional impulse. So you are adding more impulse. This increased amount of impulse is the same that your head applies, or your head supplies if the flower pot bounces from it. Consider this as an example. A 0.160 kilogram puck is traveling 5 meters per second north, and the slap shot produces a collision that lasts for 0.0020 seconds and gives the puck a new velocity of 40 meters per second south. Calculate the impulse imparted by the hockey stick. So we know that the impulse is equal to the change in momentum. The velocity is changing. We can find the change in momentum, so delta P is equal to m, or delta m times v, which in this case it's the velocity changing, so the change in velocity is the final minus the initial, and that will give us delta P, so the change in momentum. And you'll find that the change in momentum is 7.2 Newton seconds south. Okay, so the force multiplied by the time gives you units of Newton seconds. Okay, when you work it out as well, using kilograms or meters per second, you'll notice that it comes out as Newton seconds. Okay, so the change in momentum is 7.2 newtons south. Okay, make sure you're using vectors in this case. So since the puck was initially traveling 5 meters per second to the north, pick either the north or the south direction as your positive direction. So the impulse imparted by the stick to the puck is 7.2 Newton seconds. Now we can determine the average force applied by the stick to the puck. We know the time that it took for that force to be applied. Now the impulse is also given as the force multiplied by the time equal to the change in momentum. We know the change in momentum already. We can find out what that force was. So delta P over delta T. And you'll find that the force is 3,600 newtons to the south.